Welcome everyone to our third seminar. Today we are very excited to host Justin Kulp. So Justin is a postdoc at Simon Center for Geometry and Physics at Stony Brook, and he will be talking about his interesting work on holographic foliations. So Justin, thanks a lot for accepting our invitation. We are very happy to have you today, so you can take it away.
Yeah, okay. Well, thanks for having me. It's great being at, this nice seminar series you're running. And yeah, so I wanted to talk about this project I did with Latham Boyle. This is the archive number here, and you can scan this QR code if you want to you know, just tune in and kind of drop out. That's totally fine if you read the paper. In fact, you don't even have to read the paper. You could just cite the paper, and that would be good enough for me. I mean, that's no. But jokes aside, yeah. So I'm going to talk about this subject. It's an interesting, somewhat mathematical subject. I've actually gone through a lot of efforts to somewhat divorce some of the physics from the subject entirely. I will make references to physical things, and it's entirely inspired by physics. But the reason why I want to divorce it a little bit from physics or not make any too strong physical claims is because I really want to say that like all of the things in this paper that we prove are true mathematical facts, which are 100% true. And they're inspired by and have led to consequential or led to follow up work in the field of holography. You'll see the connections to holography when I go through the talk. But yeah, I really don't want to make commitments to any particular model of anything. I just want to say this is interesting mathematics, which is useful for physics. If that doesn't sound attractive, I apologize. But another aspect of this is because it's so inspired by holography, you think, oh, maybe this is only of interest to people studying high energy physics or something like that. But as you'll see, there's also connections to material science and yeah, condensed matter systems. So yeah, I'll talk a little bit about that. So without further ado, this is my plan for the day. I'll talk about an introduction and motivation. I mean, that's everyone knows what that is. Because this talk is going to use both quasicrystals and hyperbolic space, and both of those things may not be super familiar to people, I'll actually spend a bulk of the time first just talking about hyperbolic space. Then I'll talk a little bit about and quasicrystals, so beyond Euclidean lattices. Then I'll talk about the correspondence that I have in a 2D and 1D scenario where every picture is visualizable easily. I can draw them. And then at the end of the talk, I'll talk about really some of the very new things in my recent paper with Latham that are about extending this correspondence to higher dimensions, and then a conclusion. I think that's straightforward. So if you want to just scan this QR code one more time, and you don't or you need to go answer emails or something, here's the three punchlines. Hyperbolic lattices and quasicrystals, they exist. There are new quasi-periodic patterns that can be obtained by putting the two together. And there are, in fact, applications to physics, to holography, but also to condensed matter physics. So let me just go over a few of the basics. So let's just start with some historical facts. So the Sumerians in 4000 BC were tessellating their walls with clay tiles. Our entire talk today is going to be roughly about, tessellations and lattices. And in ancient Greece, Plato was discussing tessellating space with polyhedra in his theory of matter. And depending on what kind of quantum gravity circles you're in, people might still be talking about tessellating space with polyhedra. But one of the questions that Plato asked is he said, what shapes must a unit have to fill space without gaps by figures congruent to that unit? AKA, just what repeating patterns can we make out of like one type of unit cell? And this is a matter of practical importance. Of course, both the Sumerians tiling walls and bricklayers who lay bricks, which are parallelepipeds, need to know the answer to this question. So parallelepipeds are obviously examples. And in fact, Aristotle had claimed, so if you recall, there's five regular Platonic solids. There's dodecahedra, icosahedron, there's the cube, there's the octahedron, and there's the tetrahedron. There we go. So there's these five regular Platonic solids, the ones which, yeah. So there's these five regular Platonic solids. And Aristotle had actually guessed, he said, the ones that fill space, so of the five regular Platonic solids, the ones that can tessellate space or fill space, he claimed were the cube and its dual, the tetrahedron. And this is actually incorrect. It's just the cube. Only the cube can do it. And for some reason, it took people around 2,000 years to be confident in this. There's examples of mathematicians who like sort of discover. They're like, no, by whatever methods people were using in like, the 1700s or the 1500s, they would discover, no, I don't think that's right. Like it seems to just be the cube. And then somebody else would say in some written correspondence, no, that contradicts Aristotle. So it shows you what power maybe some senior people in the field might have, especially when they're Aristotle. But you can kind of forgive them, right? Because if you want to tessellate space with tetrahedron, what you're going to have to make sure, if you can see my hands, you have to make sure that the dihedral angles, the angles between faces, you have to make sure that you can put all of the tiles around a face, that you can put them around an edge and you can fill up that edge. And if you take a look at the internal angles of a tetrahedron, oops, if you take a look at them, you'll see that the angle between faces is the arccos of 1/3, which is 70.52 degrees. And so you can see that if you put 5 of them around an edge, that there would be an angular deficit of about 7.3 degrees. So it's maybe acceptable if you were just imagining with your head, if you imagine, oh yeah, it does look like maybe 5 of them could fit around an edge if I had manufactured them better. But honestly, 7.3 degrees, that is still moderately large. I mean, people maybe should have known better. Anyway, we're not here to just make fun of old mathematicians. So, one of the important concepts that you'll eventually stumble upon when you're studying these questions is the concept of a point group. So, the point groups are essentially the discrete subgroups of the Euclidean group, ED, that fix a point. And if you focus on 2D for simplicity, these are basically discrete subgroups of the group OD, right? The orthogonal group in D dimensions. And in 2D, there's going to be infinitely many of them. There's going to be Zn, just n-fold rotations around a point, and D2n, just the dihedral group, but where you include some flips. So if you include just orientation preserving, it's just Zn. Makes sense. So then there's this nice fact. So the geometric symmetries, let's say, of crystals are described by space groups. So it's not just symmetries of the plane, but it's symmetries of like it'd be subgroups that also includes like translations. So it'd be subgroups of OD, semi-direct product with RD. Okay, so you might also want to include translations. And you can see that if you have translations, this is going to further restrict the types of point groups which could potentially appear. And this is sort of systematized in the form of this theorem called the crystallographic restriction theorem. It describes which of the point groups are compatible with adding in also discrete translational symmetries. And so the crystallographic restriction theorem says that in 2 dimensions and 3 dimensions, you can only have 2, 3, 4, and 6-fold symmetry around a point. And so this infinitely many different 2D point groups collapses down into just 17 wallpaper groups in 2D, for example. And they must all have only points of 2, 3, 4, or 6-fold rotational symmetry. So here's a picture over here of a museum in Spain. This tiling here is in particular something called a rhombi trihexagonal tiling, or a P6M tiling. Doesn't really matter what that is. That's just some notation people use to label these wallpaper groups. And this has the symmetries of one of these wallpaper groups. So I want to give, this is not a proof of the crystallographic restriction theorem, but I want to sort of give at least one, it's not a full proof, but I want to prove why, for example, you can't have points of 5-fold symmetry in 2D or 3D. So the proof is quite simple. It's quite elegant. So what you could do is you could pretend, you could say, suppose for contradiction that you had a lattice and that you had a point in that lattice and it was a point of 5-fold symmetry. Then what you could do is you could take your favorite nearby lattice site, so maybe this critter up here, and when you take that lattice site, you can hit it with your 5-fold symmetry action, and that will generate the rest of this pentagon, right? Now, if that generates the rest of that pentagon, that means that all of these points, in addition to your central point, must be in the lattice. And then what you can do is you can say, okay, well, also all displacement vectors must be in the lattice. So that means if this here, the thing I'm circling here, is a point in the lattice, then so too must this point be in the lattice. So I'll maybe color it in orange. One moment. So this point must be in the lattice. But if that point's in the lattice, then I can also take a displacement vector and I can act on that, and that point will be in the lattice. And then I can take this displacement vector and that point will be in the lattice. And then this guy's going to get a little harder. I left his head behind. He's going to be in the lattice. And finally, this creature is going to be in the lattice. So you see what I've done by just having a point of fivefold symmetry is I've made a smaller pentagon inside of the original pentagon. And so as a result, you can see that then I could just repeat this procedure iteratively, and I could make smaller and smaller pentagons. And you would see that I would basically just be able to densely fill all of R2 using this procedure. So then I would have some densely packed subset of R2. Wouldn't be a very good lattice. So this is sort of the proof of why there's no fivefold symmetry. And conversely, it means if you had a point of fivefold symmetry and you had something that was a lattice, you would expect it to, well, densely fill R2. And we'll see an example of that later. Okay, so maybe we're emboldened by this. We now understand lattices and flat space. We're like very brave. We might try and go to hyperbolic space. So in hyperbolic space, or even more generally, we could even just try to tile any other surface. So we could, for example, try to tile the sphere, or if you want to say it very obnoxiously, you could say Euclidean de Sitter space, or you could tile hyperbolic space, Euclidean ADS, if you will. These are other maximally symmetric spaces, so you would expect it to be approximately as easy, or you would hope it would be easy-ish if you've already understood the plane. Now, it's actually not too bad. For example, the tilings of the sphere are closely related to the existence of 3D polyhedra, because any tiling of the sphere could really just be thought of as like some sort of polytope that's been blown outwards. It's been inflated outwards. So, for example, the soccer ball or football is a tessellation of the sphere by pentagons and hexagons. And this is sometimes also called a truncated icosahedron because it's really just this polyhedron, which is an icosahedron, which had some faces chopped off and blown out onto a sphere. Hyperbolic space is, however, much more novel. It's harder to intuit. I mean, it's hard to get a feeling of how hyperbolic space works. It has applications in art, biology, network theory, and physics. And as we'll see a little bit later in the talk, hyperbolic band theory, tensor networks, error correction, and discrete holography. So in hyperbolic space, one of the reasons why it's so hard to intuit is because there's more room. Right? If you move out in hyperbolic space, slices of, like, let's say hyperbolic space along some constant radius are of a very large area. In fact, for example, if you took some sort of limit, if you wrote, oh, that's a bad color. One moment. If you took some sort of limit, like the r goes to infinity limit of a ball of radius r plus a in hyperbolic space minus the volume of a ball of radius r, and of course normalize it by the ball volume, you know that in Euclidean space, this is just zero, right? The volume, compare how the volume grows to the surface area. However, in hyperbolic space, so this is zero in Euclidean for a Euclidean sphere, but for a hyperbolic sphere, this scales like e to the a minus 1. So you can see that the volume of spheres grows very fast as you go further and further out. And roughly speaking, this allows you to pack some more things in. So now I wanted to make some connections to physics. I wanted to also show you folks some references just to prove I'm not talking about nothing. So I'll post these in the chat, and I will also send the links afterwards for the organizer. Here are some examples of papers where people have studied discrete models of holography in ADS. This is like a huge reference dump. And it's also my excuse for not having any references in the talk on my slides. People have also studied QFT in ADS, on ADS lattices. There's this subject called circuit QED. I'll paste the references first, and then I will give a little bit of insight into some of them. There's people who've studied crystallography of hyperbolic lattices. And there's one more. There's people who've also studied tensor networks and error correcting codes. And all of these things are related to discrete geometry in ADS. And their connections, of course, to holography in some cases, but not in all cases. So let me tell you about one of them, which I think is kind of interesting. One of them is this subject I mentioned called circuit QED. And this is also, these give some examples of this is not just of interest to people studying high energy physics, right? This is of interest to people studying condensed matter physics or people studying material science. So, for example, in circuit QED, what you have, here's an actual picture. This is an actual photograph of one of these circuits in the circuit QED. So what these things are is this is a lattice of superconducting coplanar waveguides. These are just some waveguides, okay? And the idea is that you can have microwave photons that travel down these waveguides. And the purpose of this circuit QED is you basically use these waveguides to simulate sort of artificial materials for these microwave photons. And in particular, you can simulate weak or strong, like you can simulate QED, things that behave like QED, but with different values of alpha. So you could, for example, simulate QED with a strong value of alpha. So alpha QED could be simulated much greater than 1, for example. Okay. And this lets you like understand in some solid state systems, like somehow like a strongly coupled version of QED. This is a picture here of what essentially the geometry is of this lattice that's engineered over here. And yeah, that's good. And in some of the references I dumped in the chat, I also gave some examples of people who've studied hyperbolic band theory. So you'd imagine that if you're on a hyperbolic lattice, or you're in a material in hyperbolic space, that you wouldn't have usual block theory. You wouldn't have your usual sort of Bragg theory. You would have some sort of more complicated version of momentum space.
Can I ask a
Sorry,
question?
I have yeah.
Yeah. Both of you, please. Yeah.
The other person can go first if you want to.
Sure. I wanted to ask, like, when you're like trying to simulate something on a hyperbolic lattice, one of the first things that would come to my mind is that you would have severe boundary effects because your boundary and the bulk, they are growing at the same rate. Like, do you have any comments on that?
I don't. Yeah, that sounds very interesting. Let's see. By and when you ask about the simulation, you mean specifically like you don't mean trying to engineer it in a material. You mean, for example, if you tried to put it on a computer or something.
Both, in fact, like just in
Oh,
case.
okay. Yeah, no, that's an interesting point. I legitimately had never considered that. I assume since people have done it in some of the references that I I linked many references, so I apologize. I can't point to any one of them. But in one of the references, I mean, I guess they must deal with this some in some way. But actually, sort of the entire point of today's talk is going to be to describe a certain boundary, special quasicrystal that appears at the boundary of these things. So in maybe this isn't an answer to your question, but just a tantalizing future comment is, I hope to tell you exactly what the geometry of these boundary objects is. But yeah, sorry. Is there another question?
Yeah, so I wanted to ask, like, so you mentioned this circuit QED. Is there a version of that for non-abelian versions like
Uh,
QCD?
I have not seen that. I don't know how one would engineer that. I read the Circuit QED papers a long time ago. I don't think it's possible, but I'm not as
Hmm.
clever as these Circuit QED folk. Um, Yeah, I'm unsure. I mean, maybe somebody could do it. Maybe you could do it. Uh, I can't do it. I just don't know though. I'm not. Yeah, yeah. So, okay. If
Sorry,
there's
one
no,
more
yeah,
comment. Yeah,
sure.
one more comment. Like when you said like momentum space, I think momentum space may not be the correct way to think about it. It would be something like a melon space, just a technical thing I
A-
want
a-
to say.
Yeah. No,
So
I mean,
yeah,
absolutely. It's definitely not traditional momentum space
momentum
because you
space. Yeah.
don't, yeah, you don't have this usual relationship between exactly. Yeah. So you might imagine if you're, yeah, familiar with usual ADS CFT or something like this, that yeah, it would be something more related to the, harmonic analysis
Yeah.
on ADS. Not, yeah, I fully agree. Momentum space in scare quotes.
Yeah. Yeah.
Yeah.
Also, one of the things, like, sorry, just to say, like, even for the simplest case of hyperbolic lattices, I think getting the like all the eigenfunctions are very difficult to find. I
Yeah.
tried that. That's why I'm saying.
Yeah, absolutely. In one of the first in the clump of references, a crystallography of hyperbolic lattices and hyperbolic band theory, there were a number of people who've tried to work this out. It becomes very complicated because, translations are roughly speaking non-abelian. So it leads to a bunch of complications. It gets very messy very fast to solve very simple problems. There's a number of authors in those work, but I really want to highlight in particular of those references the work by Stephen Ryan, some Canadian mathematicians and physicists in Saskatchewan and Alberta. Yeah, if you see those names on the papers, I highly recommend their paper. Stephen Ryan and the last name is something like Makijo. I can't say it correctly, but you'll see it if you see the names. Yeah, it's a good comment. Okay, so that's some comments about hyperbolic space. Let me move forward because I mean, they're great questions, but I guess I should move forward. Um, this is something I'm going to go through it fast for the sake of time. It's not the best way to understand quasicrystals. It usually just leaves people confused. But I think it shows just how bizarrely connected quasicrystals and aperiodic tilings are to just random subjects you would have never guessed. So I'm going to start with a very simple question. I'm going to say, given a set of prototiles with rules that colors must match, can you use them to tile R2? What do I mean by prototiles? I mean, you have some fundamental set of objects. Maybe they look like this. In my case, let's say you're not allowed to rotate them, but you could also ask the question with rotations. So this is my set of prototiles. You're allowed to clone them. You're allowed to copy them and move them around and try and tile R2 with them. And then the question is quite simple, right? Given some arbitrary set of prototiles, is there an algorithm to determine if that set of tiles tiles the whole plane, tiles R2 without any holes or gaps? So you have three options. Well, really you have two, but we're going to artificially separate into three. The prototile set does not tile R2, no matter how hard you try. It's not hard to cook up an example of a prototile set that doesn't do that. Just put like something where you maybe fill in just one box like that. Certainly these prototiles would never tile R2 because you would never be able to match this color here in red against anything else because everything else is white. Okay, so it's very easy to see that options in species one exist. This prototile set, they tile R2 and they admit a periodic tiling. It's also not hard to see that examples of that type exist because you could just take the tile, which is just one solid color. And those would obviously do that. And then there's a third option. The tiles, they tile R2, but they never produce a periodic tiling. In other words, that tiling set is called an aperiodic set. Okay, and you're like, okay, that seems like a funny thing. This question was actually originally asked by some logicians in like the 60s. And Hao Wang, the logician, he proved the following. He said, there exists an algorithm to determine if a prototile set tiles the plane, if and only if all possible prototile sets are of type 1 or type 2. Okay, seems very strange. For some reason, the existence of aperiodic tilings is connected to the ability to understand if there's an algorithm that determines if a set tiles the plane. And then his student, 5 years later, proved the following. There is a map that takes you from a set of tiles, takes you from Turing machines to the set of tiles. So somehow you feed it in a Turing machine, which is like an abstract computer, and then it tells you, it gives you a tile set, and that's it. And this map, so it has the following property. M halts, the Turing machine halts, if and only if the tile set tiles the plane. And so this proves aperiodic tilings exist. The logic is maybe a bit fast, but the reason is as follows. There's a famous theorem that says you can't determine if M halts. That's called the undecidability of the halting problem. This is a famous problem in computing theory. And therefore, by Berger's theorem, you can't determine if tau M tiles the plane. And then, therefore, by his supervisor's theorem, since you can't determine if tau M tiles the plane, not all tilings are of type 1 or type 2. So not all type 1 or type 2. 1 or 2. And therefore, you conclude that aperiodic tiles exist. It's not a constructive proof, but yeah, I think it's just really funny because it shows you somehow these aperiodic things are linked to some very deep and interesting problems, even in like pure logic. So what is a quasicrystal or an aperiodic tiling? Quasicrystals are aperiodic tilings which still possess some order. Yeah.
Can I
Is there a
ask
question?
Yeah.
Yeah.
Yeah. So if I take like the space of all the possible tilings, like which one is more? So am I more likely to get the aperiodic tiling or periodic tiling?
I honestly have no clue. I don't. That's a great question. I don't know if it's been studied. That sounds like an insanely hard problem. Let me see. I'm just trying to think. I don't have an answer, but I'm just trying to think. I mean, I think possibly some people studying non-commutative geometry might have some answers to this problem. Alain Kahn has been interested in these sort of questions, but I genuinely have no clue. It's a great question, and it's in the spirit of some later things. Yeah.
Can I comment on this, please?
Yeah.
So this Turing halting problem and the computability of real numbers, as far as I know, is intimately related. And almost all real numbers are not computable.
I see.
So maybe there's also a similar situation here that there is a vast number of aperiodic sets that.
Yeah, you know what? That's a good point. And actually now, I mean, intuitively, to even go to say it in a way that's even simpler, um, you would expect there to be far more aperiodic sets because you could just take any periodic tiling, like any periodic set, and it seems very easy to just mess it up, so to speak, by just like adding some like just like deforming it slightly. I guess you'd have to still make sure it tiles are too, but it actually would seem here's an even simpler way of saying it. You know, it's very hard to construct a lattice because you have to have like this infinite regular ordered procedure, but it's very easy to produce an aperiodic lattice because all I have to do is grab one of those points and just move it, like move one point in a gross way, and that would just immediately break it. So a priori, my I would say that would be my sort of it'd be nice to quantify it though if there was some way to quantify it. So
Well, there are far more real numbers than rational numbers. That's what you're saying.
yeah. That's yeah. I guess that would be like the one-dimensional version of the problem, maybe. Um, Okay, yeah. So great questions. Yeah, so let me tell you a little bit about quasicrystals. So quasicrystals are aperiodic tilings which still possess some order. So by aperiodic, I mean they have no translation symmetry by any amount at all in any direction. Um, and so quasicrystals are aperiodic tilings, but again, they still possess some order. So they're somewhere between ordered systems like regular lattices and completely amorphous things, right? Um, so, yeah. So these quasicrystals, whatever they possess some sort of classically forbidden symmetries, which spoil many classical intuitions. So, for example, here's a diffraction pattern of some material. I didn't write down what that material was. This is a diffraction pattern, and if we take a look at this diffraction pattern, we can see that the diffraction pattern has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it has a point of tenfold symmetry. You can take a look at this pattern. And we saw earlier in our talk that points of fivefold and tenfold symmetry can't exist in usual lattices. Okay, so there's something going on here, and indeed, one of the ways that these quasicrystals were kind of originally developed or understood was Dan Schechtman in 1984 had studied some sort of material in the lab. He has a paper. It's called "Metallic Phase with Long Range Orientational Order and No Translational Symmetry." So he wrote this paper in 1984, and he was eventually, oh, maybe I'll write his last name, Schechtman. And he eventually received the 2011 Nobel Prize in Chemistry for this discovery. And in Dan Schechtman's work, he basically obtained some diffraction pattern. I don't think it was this image I picked here. I picked some other materials which people have since discovered, which have cleaner images of their diffraction patterns. And he basically just realized they couldn't possibly correspond to translation standard lattices because of their diffraction patterns. Actually, curiously, there was some doubt about whether or not the pattern was actually from one of these things called a quasicrystal. Maybe it could have been something else. But, oh yeah. But it turns out that what people were able to do is they were able to, in modern times, we could just go out and we could find one of these materials. And now, what is a diffraction pattern? A diffraction pattern's a picture of momentum space. And we could actually go and we could just take real space pictures now using scanning tunneling microscopy. And they found some material, which was a candidate quasicrystal. And you can see, I mean, if you'd have to really zoom in, but you can literally see that here, like these little white dots you're seeing are actual pictures of like actual atoms in the lattice. And you'll see that they indeed have points of local points of fivefold symmetry, rotational symmetry, local points of fivefold rotational symmetry. So they're not, yeah, so you can actually take real space pictures now. It's quite remarkable. This picture was actually a picture from a real quasicrystal. So, and by real quasicrystal, I mean one not made in a lab. It's a natural quasicrystal is maybe a better way of saying it. So this was a picture, Paul Steinhardt, the cosmologist at Princeton, him and some other folks went to a meteorite impact site in Russia, and they believed that it should have had a quasicrystal. And then they took this material, and this is a picture of that material from that impact site. So they show up in many places. They show up in meteorite impact sites. They can be built in labs, found in nature. They show up in condensed matter theory. People love studying spin systems on these things, and also in statistical physics, studying topological phases. They show up in math. We saw in logic previously and non-commutative geometry. This was also something I alluded to in a previous question. And they show up in high energy physics. There was a while where they showed up in the form of certain things called quasicrystalline compactifications in 2D CFT. You know what, for time, I won't go too much into that. And then also possibly they show up in discrete holography, and that's the point of the rest of the talk. So just to recap our introduction, I promise I'll speed things up and there'll be lots of pictures. We've kind of understood classical crystals. I'm going to spend a little bit more time systematically talking about hyperbolic lattices and talking about quasicrystals. And then, motivated by the ADS CFT correspondence, I will talk about how there's a relationship between hyperbolic lattices in D+1 dimensions and quasicrystals in D dimensions. Okay, so again, these are just the outlines and punchlines. Hyperbolic lattices and quasicrystals exist. There are new quasi-periodic patterns that will come from this procedure, and there are applications to physics. So yeah, maybe what I'll do is I'll send one more clump of references, and these include some overlaps with references I sent previously. So let me send them here. So in particular, these references are all about, in the first reference is the original sort of discovery of my co-author and his collaborators, where they discovered this sort of relationship between regular tessellations of hyperbolic space and quasicrystals. And then all of the subsequent papers are examples where people have since used it in physics to test things. So for example, I want to highlight, for example, the work of Joanna Erdmanger and her collaborators, where they show, for example, if you take a hyperbolic lattice and you study some spin system on it, and then you have some sort of natural quasi-periodic structure which appears on the boundary. There's some lattice model there, and you have some holographic relationships between the two. So, for example, they can reproduce the BF bounds in ADS CFT numerically by studying these things. But again, for us, we're just going to be mostly mathematical. So let me talk.
May I ask a question, please?
Yes.
Well, look, I would like to ask a more down-to-earth question.
Mm-hmm.
For example, you can take coal and you can do a phase transition to diamond. Coal is amorphous and diamond is a crystal.
Mm-hmm.
And I'm wondering if there's a phase transition from quasi-crystal to crystal order. And my question is more about ground state. Can I have ground state being a crystal, or is it true that this is a false vacuum? And then if you anneal it properly, does it eventually go to a crystal state at a lower energy? So phase transitions and ground states in crystal systems.
Yeah, that is a great question. Yeah, so the answer, as far as I know, is to the first part of the question is like, can there be sort of maybe like quasi-crystalline phase transitions or something like that, if you want to use that term? The answer, so far as I know, I think is yes. I think there was recent work maybe by, I don't know if Slava Richkov was part of it or one of his collaborators for sure, Junshin Rong. There are people who are kind of studying these things in recent times. I think there are many physics papers about this, but I don't have any offhand. I'd be happy to help find some later if that's all
So
right.
can I have quasi-crystal to be the true ground state of the crystal, of the atomic system?
I mean, I guess the answer must be yes, because there are, for example, macroscopic quasicrystals, and it doesn't seem obvious to me that they would suddenly just become ordered lattices in any.
Yeah, sometimes it's false vacuum. Sometimes the systems are glassy, for example. It's not true ground state, but it lives on forever. You have to anneal it. Similarly, coal, right?
Mm-hmm.
Obviously, diamond is ground state.
Right. Now, these quasicrystals oftentimes have lots of, in a way that can be made precise, but we won't go too much into this. They have some forms of long-range order. I don't know if that would protect you further. I mean, again, I guess it could still be some sort of false ground state or vacuum state. But I suspect this would protect you from tunneling even further. So yeah, it would seem very hard to have a, yeah. I don't know, but that's a good question. Yeah. I suspect these things must be actual. Yeah. For example,
condensed matter physicist. So that's the first question that comes.
Yeah. Yeah. So, for example, would your for example, if it was a false vacuum state, then would it be that at zero temperature you would expect it to turn back into a standard lattice?
No, what would happen? You anneal it, you heat it and cool it back. It will go back
Mm,
to a crystal state, for
I
example.
see. I see. I see. I see. Um, okay, yeah, that's a very interesting question. So in some sense, it'd be like, do the atomic components of these quasicrystals, yeah, if you cooked them back up and let them cool back down, would
Right.
they? Right, right. You know what? But here's just a
Or I take a
speculation.
hammer, right? I forge like forging the steel. I take a hammer,
Yes.
you hit it and heat it and cool it, and suddenly it disappears, for example.
Yeah, that's a good point. Now, I note that again, one of the places this was found in nature was at a meteorite impact site. So I would have thought that that would have been sufficient, sufficient heating.
Look,
But I
then I
guess
say glass because you can also find glasses after
that's
volcanic eruptions, but glass is not the
that's
true
true.
vacuum.
That's true. That's true. And you can also find it at like nuclear blast sites
Yeah,
and
yeah,
whatnot. So
exactly.
yeah, it's a great question. Yeah. Um, yeah, another great question. This subject is somewhat like it's existed for a very long time, as everyone can see. It's existed since the 60s, so at least 60 years. And there's been like intermittent studying of the problems, but I don't know if there's like yeah, it's not been super systematic. So there's been some systematic work, but not yeah, it hasn't received as much attention as other materials. Okay, I will move on because I guess we're running short on time. So I'm going to do this a little bit faster now. So
Actually,
yeah,
Justin, if you
yes,
have
sir.
time, we can go on further. Like you don't have to finish in 45 minutes. I mean,
Okay, I
it's up to
mean,
you, but
yeah, I'll still aim to get all of the. I'll try to save my research for after the hour mark, or like the really technical stuff about
okay,
higher
it's up
dimensional
to you.
stuff. Yeah, thank you though. Okay, yeah, so I just want to talk to people about regular tilings in 2D a little bit. So we're just to set some notation. So in the Euclidean plane, the angle of a regular p-gon, which is denoted like this in these curly brackets, curly p, is 1 minus 2 over p times pi. This is the interior angle at any vertex. And so in order to tile all of R2, you just have to make sure that you can fit all of these little creatures around any particular vertex. Right? You have to make sure that you can fit all of the angles around a vertex. And so what you'll see is that the regular tilings of R2 are what are denoted 3, 6, 6, 3, and 4, 4. And let me explain that notation. What this means is the first notation, so if you have PQ, what this notation says is that you have regular p-gons, so p-gons. And then the second piece of notation says Q fit around a vertex. This is this notation. It's called Schlafly notation. And so in the Schlafly notation, for example, over here, you have a tiling by hexagons. So those are 6 gons, and you can see 3 of them fit around a vertex. So this would be denoted 6, comma 3. The coloring is irrelevant. It's just to make it look, I guess, kind of tasty, like a nice berry or something. Um, And then in higher dimensions, you can see that there'd be a similar problem. In higher dimensions, you must make sure, as I was mentioning at the start of the talk with the tetrahedra, you must make sure there's going to be angles between faces, and you must make sure that that the angular deficit is such that angles can fit around an edge. Some number of angles can fit around an edge if you want to make a regular tessellation. Before I go to higher dimensions, though, let me tell you a little bit about hyperbolic space. So in hyperbolic space, angles of the regular p-gons, they gradually decrease to 0 as the edges get bigger. They sort of become more and more sharp and pointy. Ooh, that color doesn't show up very well. They sort of become sharper and pointier as you reach out to the boundary. And so as a result, you can tune p-gons to fit around a vertex. And there's a general theorem that says the following. If you have a PQ tessellation, as I mentioned before, and 1 over P plus 1 over Q is equal to 1/2, then you tessellate the Euclidean plane. You can check that there. If it's greater than 1/2, you tessellate S2. And if it's less than 1/2, you tessellate H2. So here's an example of all these tessellations. So here's the ones where it's greater than 1/2. And you can see what you have is you exactly obtain 3, 3, 3, 4, 4, 3, 3, 5, and 5, 3, which are also the regular Platonic solids. It's related to the comment I made earlier. The tessellations of the sphere are related to just blowing up polytopes. And so regular tessellations of the sphere are related to blowing up regular polytopes. Here's the tessellations again of the Euclidean space. There's also a finite number of those. And then basically everything else tessellates H2. And they always look like some sort of MC Escher picture. Here's an MC Escher picture down here in the bottom right-hand corner. Now, we could go to higher dimensions, and let's focus on hyperbolic space. So in hyperbolic space, we've seen that if P and Q are less than 1/2, 1 over P plus 1 over Q is less than 1/2, you tessellate H2. And then there's also tessellations of H3, H4, H5, and HD. Let me explain this notation just one more time. So this one here says you have foregons. Then 3 of them meet around a vertex. Let me say a foregon. 3 meet around a vertex. And then 5 meet around an edge. So you can see very clearly here, if you have a foregon and 3 meet around a vertex, that's just a cube. You even see it's in my pictures here on the previous slide in the middle. And then if you have 5 of them meet around an edge, well, this is a quirk of hyperbolic space. For example, if you had 4, 3, 4, that would be the tessellation of Euclidean 3-dimensional space by cubes. And this is 4, 3, 5. So you can somehow, in hyperbolic space, you could pack in an extra cube by tuning the edges and vertices just right. In particular, let me highlight one of these tessellations. Let me highlight the one that's called 353. The 353 is a tessellation of 3D hyperbolic space by icosahedra. 3,5 is a icosahedron, and then you can fit 3 around an edge. Okay, and this picture over here on the right is a picture that somebody drew, or it's on Wikipedia as well, you can find it there, is a picture that somebody made where they basically simulated as if they were inside a piece of this 353 tessellation. There's a curious fact, which I note, which is, I think it's very interesting, is that, people are usually very surprised by this, is you can also find the tessellations in H4. There's some finite set of them. You can also find them in H5. Now, in H5, if you want to find any tessellation, you have to have non-finite cells and vertex figures, which is just a fancy way of saying, like, you can have them, but for some reason, you have to have that, like, one of the shapes, it can, like, kiss all the way out to the boundary. And then if you go greater than 5 dimensions, there's just none at all. So really, for practical purposes, they really exist here. They exist here in some mathematical, fantastical way, and they just definitely don't exist in higher dimensions than that. There are other tessellations, but you can just never find regular ones. It's a curious fact. Here's some pictures of people who got their hands on 3D printers, and they also tried to print this 353 tessellation. The 353 tessellation is not, sort of my favorite tessellation because it's the one that's most intimately related to Penrose tiles. So now let me return one more time to quasicrystals. So I told you before,
just quick question. Like, is it only true for hyperbolic tessellations? Can you tessellate a higher dimensional sphere or a Euclidean space in any dimensions?
Yes, you can tessellate Euclidean space in any dimension with a hypercube. With the sphere, I don't have the list memorized. There is a paper. So all of this, in particular, these tessellations of regular hyperbolic space was done in a famous paper by Coxeter. And he also had a separate paper where he talks about tessellating, I think he refers to them as elliptic spaces, which includes the sphere. And there he has the list. I actually don't have the list memorized. I apologize. But if you just look up Coxeter regular tessellations of the sphere, you should find the paper. It'll have approximately that name. It's a good question.
If I cut this higher dimensional tessellation and do a projection on the cut plane, do I get anything interesting?
That's an amazing question. That is the entire purpose of the second half of the talk. The short answer is absolutely yes. Yeah. So let me talk just a little bit more about quasicrystals, and then I'll race through some other things. And then in the spirit of that question, I'll jump to that answer very quickly. I'll skip over some of the more mathematical asides. I just also love talking about the subject because these are subjects which get little attention. So this is my chance to do some outreach for the quasicrystal community. So yeah, I mentioned before there's sort of this definition of quasicrystal, but it's a little bit nebulous actually. There's no agreed upon definition of what a quasicrystal is. One of the definitions that people do use is they define them by their diffraction patterns. They say, for example, the reciprocal lattice is spanned by integer linear combinations of greater than d basis vectors in d dimensions. So they sort of have more Bragg vectors than dimensions. And this is related to the fact that their diffraction patterns should sort of densely fill fill the plane or whatever space you're looking at. Now, since there's no agreed upon definition, it makes comparing literature a little hard, but let's make the following claim. Whatever definition you use of a quasicrystal, you should probably include the Penrose tiling. It's like the most important one. The Penrose tiling is this creature over here on the right. And there are many ways to create a quasicrystal, okay? So different constructions highlight different properties that they have. So let me just tell you about a few. There's local matching rules. We kind of saw that earlier with the example with the Wong dominoes, those ones related to the Turing machines. Here's the example of the two that make a Penrose tiling. There's a thick rhombus and a thin rhombus. And the rule is you have to match them, and you have to match the orientation and species of arrows on the edges. There's these things called almond lines, which really highlight their long-range order. That won't play an important part in today's talk, unfortunately, but it's extremely interesting. There's the cut and project method, which is related to the previous question, where you take a higher dimensional lattice and you cut it at an interesting angle and you project onto a subspace, and then you look at the pattern that appears. I'll go over that in a second. The one that's most important for today's talk are substitution rules. Substitution rules are nice because they really highlight the aperiodicity. And then finally, there's the so-called pentagrid method, and it really is important for understanding defects. So let me just talk briefly about this cut and project method. It's actually not the most important for today's talk, although it is related to the previous question, and we'll see why maybe later if we have time. But this is the most common. For some people, this is the definition, especially if you're a condensed matter theorist. This is how people define quasicrystal. So what they'll do is you'll take a regular tessellation. So here I've taken the square tessellation of R2. And you take a regular tessellation, and then what you do is you take a line and you cut the regular tessellation on this line. And you cut the regular tessellation on this line and you pick it to be at an irrational angle. By irrational angle, I mean like theta is equal to, for example, square root 5 pi or something like that, right? So it's at some irrational angle in multiples of pi. So it's at this irrational angle. And then what you do after you've taken this cut is you fatten it up. Usually you fatten it up, let's say, into the width of 1 unit cell. And you imagine taking all the points inside this 1 unit cell. So that's what's colored there in orange. And then you take all of those points, which are in that sort of fattened up band, and you project them down onto the 1D cut surface, or just you project them onto some cut surface. And what you'll get is you'll get some pattern that looks like this over here. There's a deep relationship. So for example, here you can see there's a long creature, short, long, long, short, long, short, long, long, short, long, short, long, long, short, long, long. So you get some 1D tessellation in terms of these longs and shorts. And this is a systematic procedure for producing producing a quasi-periodic pattern. You might say, why did I get 2 species of longs and shorts? This is related to the actual angle you cut at. It has to do with the fact that you took a square root of 5. It has to do with this fact that that there was a square root. This relates to some deep number theoretic properties of quasicrystals, which I definitely don't want to go into. But you can find more in any standard references on quasicrystals. You might ask, is the Penrose tiling obtained by cut and project? It's obtained by cut and project, yes. So yes, the answer is yes. It's obtained in different ways. One nice way to obtain it is you take the A4 lattice. If you're familiar with like Lie theory or something like that, you've definitely seen the A4 lattice before. You take the A4 lattice. It's also the root lattice, I guess, for SU5. You cut it. It's a 4-dimensional lattice. So you cut it on a plane at a certain irrational angle. Okay, I won't go into too many details. And then you can project down onto it, and you can find the Penrose tiling. There's also another way to produce quasicrystals, and that's the substitution rules. This one's extremely important for us because it's intimately tied to their aperiodicity in a very nice way. So what you do with this is you start with a finite set of prototiles. So here's again our friends, the thin and thick rhombus in the Penrose tiling. And what you do is you say there's some procedure for blowing them up. You size them up and you slice them into smaller creatures like this. Smaller versions of themselves. This factor that you blow them up by, this is called a scale factor. It's usually not unrelated to those irrational numbers that showed up before. So for the Penrose tiling, the scale factor turns out to be the golden ratio. It's like 1 plus square root 5 over 2. And this is, again, intimately related to some number theoretic properties it has. Here's an example of how you might use this in practice. You might take some little finite patch of tiling, and then you just keep systematically blowing it up bigger and bigger, and then you take the limit as n goes to infinity. So whenever you have these substitution rules like this, it implies an aperiodic set. Let me go very briefly into the details. So start with a finite set of possibly decorated prototiles, abstractly called T1 through Tn. And suppose there is, and this is critical, suppose there is a unique rule for grouping together these prototiles into larger supertiles with some scale factor lambda. If that's the case, and this uniqueness is extremely important, if that's the case, then you can prove that tau is an aperiodic set. The proof is actually pretty straightforward, but maybe for the sake of time, I won't go into it. But I'll just assert to you that the Penrose tiling, it has two prototiles, and its supertiles have this property. And also I should mention, somehow the irrationality is an important property. It's not necessary for this aperiodicity, but it's somehow another important feature of this. It has to do, yeah. Okay. Let me give you a non-example just to show the following. So for example, obviously squares do not form, like just regular squares do not form a aperiodic set. Okay. And that's because there is no unique way to locally group together an unmarked square tiling into larger squares. So you can sort of have domain walls form, right? Because imagine you sent out, I guess in modern times, you'd send out like a swarm of drones and you said, okay, guys, you have this square tessellation. You have to group them together into bigger tiles. What are you going to do? Well, your first drone, he might go out and he might sew these guys up together. And, you know, one of your other drones, he might sew this guy together up here, or maybe even better, he sews together this guy up here. But then you have some other drone and like he didn't get the memo and he goes out and he sews this one up. And what you see then is now because of that, these you cannot possibly complete these together into a bigger tessellation by squares, right? You have your one drone kind of ruined it for everyone else. And so this is very important. There is no unique local way in this to group these things together. But in an aperiodic set with these defined via these substitution rules, there is a unique local way to do that. And that's perhaps the most important thing. I'll skip the rest of the details of the slide. That's the most important thing. This is a nice property of Penrose tilings. You know what? I will go into it because it sort of explains why you might expect that there's a relationship to like conformal symmetry or at least scale symmetry. So you might ask yourself sort of this mathematical question. You might say, how many Penrose tilings are there? Right? And it turns out mathematician John Conway proved there are an uncountable infinity of Penrose tilings. Okay, so Penrose tilings, so you might say, okay, so when you look at this picture, you're just looking at one Penrose tiling in this infinite set. But then, miraculously, they have another property. All Penrose tilings are locally indistinguishable, which means any finite size patch of tiles in one can be found in any other. So that means you said, oh, you only showed me this picture, this one boring picture of one Penrose tiling in this infinite set. You've really disappointed me. And I say, no, they're all locally indistinguishable. So I've actually shown you a finite patch of every one of this uncountable infinity of Penrose tilings. You can find this patch and any patch that looks like it in any other Penrose tiling.
Can I ask a short question here, please?
Yes. Yeah.
So can I prove the other way around? Can I say that if I have a quasi-periodic system, is it always the case that it is cut and project of a periodic higher dimensional lattice?
Right. That's a good question. So So there's a vacuous answer and there's a more interesting answer. The vacuous answer is if you take as your definition of quasi-periodic tiling, things obtained by cut and project, then the answer is obviously...
Okay, specifically Penrose tiling. Is every Penrose tiling a cut and project of a higher dimension?
Yes, it is.
Yeah. In that case, this theorem is obvious because there are infinitely many irrational numbers. Every choice of them gives you a different Penrose tiling, and irrational numbers are normal, so you can sample numbers. Like locally, they are indistinguishable. So every sequence appears in pi, also in E, for example.
Yes, although, if you cut it at some irrational angle, right? It's not just irrational angles that you can cut it at. You have to, right? If you cut it at an irrational angle that's related to, I don't know, the 45th root of 17, you wouldn't expect that when you cut and project that you obtain the Penrose tiling. So that's one obstruction. And the other obstruction is you also would have to understand when you do this cut and project, you also have to understand. I mean, I agree that this would be one method of proving this fact. The proof of Conway is actually very cute as well. But another thing that you'd have to prove is you'd have to prove, like, how do you know if you took square root 5 and then you also took like 1 plus square root 5? How do you know that those don't produce, the same tiling, for example? So it is a little more subtle, but I agree. There's some nice techniques that you could use there. Good. Now, but let me also answer the specific question that you asked. So if your definition, for example, of a quasi-periodic pattern is, does it have more than one Bragg vector, let's say in one dimension, that would be like a 1D quasicrystal, or does it have greater than D Bragg vectors in D dimensions? Then you can prove already in 1D that not all quasicrystals are obtained by cut and project. So there are other things that you might want to call a quasicrystal by some other definition, or by that definition, which are not obtained by cutting and projecting higher dimensional lattices. That's not a proof against your claim about the Penrose tiling. That's just saying more generally, the world of quasicrystals is probably bigger than the world of cut and projects. But the Penrose tiling is very distinguished. So yeah, great question. So I also want to point out that Penrose tilings, they have some sort of local scale symmetry, right? Because you can take any Penrose tiling, let's say in this purple, and then underneath in this salmon pink color, you can take the tiling, you can decimate it, and you can rescale it by lambda. And this new tiling is locally indistinguishable from the original, but generically globally distinct. Actually, it's always globally distinct, but that's not an easy proof, trust me. So in some sense, there's always some sort of local scale symmetry or there's some sort of scale symmetry, because you can do this decimation procedure and then you get something which sort of exists in some way to the previous mother pattern. So you can see it's sort of, if regular lattices sort of discretize translations and a bit of rotations, these Penrose tilings, they sort of discretize scale transformations. So let me just summarize all the background, which I spent the entire time talking about, and then I'll lightning fast go through research. So hyperbolic space exists. You can tile it with regular tessellations. There are infinitely many in 2D and a few more in higher dimensions. Quasicrystals exist. They're aperiodic, classically forbidden symmetries, and they have long-range order. Many constructions exist, but the most useful for us is this concept of the substitution rule, this local, unique, invertible rule. And the most famous example is the Penrose tiling. So here's a hyperbolic space, and here's a Penrose tiling. Brilliant. So let me tell you a little bit about the procedure that we actually propose for understanding these quasicrystals. So the following is a picture of the 7-3 tessellation and the 3-7 tessellation. They share an underlying tessellation by triangles. They're related. And so here in black, I've also highlighted it with my yellow highlighter. You can see that I've drawn a finite-sized patch of the 7-3 tiling. So I got a little key over here. So then what you can do is there's a very obvious prescription for growing this patch of tessellation in the bigger bulk dual tiling. So you can grow it into a clump of the 3-7 tiling as follows. So let me highlight it. I'll go very fast. So you can grow it into a bigger picture of this 3-7 tiling. And what you'll just do is you'll just adjoin onto the picture any triangle in the 3-7 tiling, which touches the 7-3 tiling at least one point. This is obviously not the unique way to define this growth rule, but in some abstract ways, which I will not go into, you can argue that any other thing is approximately equivalent to this. Now I'm going to just play a game, just for the sake of it. I'm going to go and I'm going to walk around the boundary of the tessellations, and I'm going to label the boundary vertices by how many things in the bulk they touch. So in red, I will label the 7-3 tiling. So I'm in the yellow tiling. I don't see the blue tiling at all. And I come to a vertex and I call it 1. I call this 1. This guy here is connected to 2 things in the bulk, this heptagon and this heptagon. So he's called 2. And I keep going around 2, 1, 1, 1, 1, 2, 1, 1, 1, 1, 2, 1, 1. I could play the same game in the blue tiling. I could walk around its boundary and I could label its boundary vertices 2, 2, 3, 2, 2, 2, 3, 2, 2, 2, 3, 2. Okay, so I have some prescription for growing things in the bulk, which is pretty natural. I have a prescription for labeling boundaries, boundary strings of these 2D tessellations. It seems natural-ish. I mean, you might say there was other ways you could have chosen to label it. I argue, but will not prove. You can kind of argue it. We kind of argue it in the paper that this labeling is essentially unique. It's unique up to a correct notion of uniqueness for quasicrystals called local equivalence. I wouldn't go into it too much. I just say it's essentially unique up to the right notion of uniqueness. So now we take a look at these two things. We've got these procedure for growing things in the bulk and this procedure for labeling things on the boundary. And you might ask yourself, is there any way to sort of obtain the red labeling of the 7-3 tiling? Is there a way to obtain the red labeling and use it to get the blue labeling? And the answer to that is kind of yes. I mean, if you just squint your eyes and look, you see that roughly speaking, it looks like if you had a 1 down here in this layer, let's say in red, that it sort of turned into this 2 up here and this 2 up here. So I don't know, maybe the right way to write it is like it turns into half of the 2 on the left and half of the 2 on the right. I can go into those halves if you want, but it's not something you should be too afraid of. And then you look and you say, oh, if I have a 2 here, it looks like he kind of turned into a 3. And yeah, it looks like he kind of turned into a 3, but then for some reason, oh, sorry, this should have been a 1. For some reason, it looked like this guy here, he contributed half of this 2, and then he contributed like half of that 3. No, that seems wrong. So it seems like what 2 does is he like deletes half of a 2, so minus 1/2, produces a 3, and then produces another minus 1/2. And you might say, oh, what is this witchcraft? Like, this is pure numerology. What does it mean to have half a tile? What does it mean to have inverse half of a tile? It seems, again, like totally like witchcraft. You can actually work in conventions such that these factors of 1/2 and these negatives never appear. I just prefer to use this notation because it's more symmetrical. So I just claim, just by experiment, just by observation, that there exists some way to take a look at boundary strings in the yellow patch and produce boundary strings of the blue patch. And you always get the correct answer. And note that all you need to do to understand the local behavior slightly above, like in the layer above the other creature, is you just need to know the local behavior of the creature below. So it's basically saying that the growth of these regular hyperbolic honeycombs is sort of contained in its boundary information, and the growth rules are essentially local. You can try and construct counterexamples to this. We address that also in the paper. So you can kind of try to come up with a general rule. So you can imagine you had some sort of abstract P comma Q surface. Here it is here. And you could say, okay, what is the general rule? Well, what you do is you come to some vertex, and I call it an N vertex because it's connected to N pgons that meet here. And then you'd say, okay, I'm going to try and grow it. I'm going to try and grow it into the QP surface, in blue. And so what I'm going to do is I'm going to take a qgon, and it's going to come and it's going to wrap around that N vertex there in the next layer. And very roughly speaking, you can see that what's this going to do? Well, in that qgon, you can see that N of them are necessarily submerged down here. N of its vertices are submerged. Here in black, these creatures are going to be shared with whatever qgon gets adjoined over here. And up here, you're going to see that there's just a whole bunch of 1 vertices. So you'll see that in general, the general growth rule is that an N vertex turns into, in scare quotes, half of a 2. It turns into Q minus N minus 2, 1 vertices, and it turns into half a 2. And again, I assure you that these numbers of 1/2, they're mathematically useful, they're symmetric, they're very beautiful, but they're not necessary. And we explain in the paper how to get rid of that. And so this gives you some general rule of how this would work in a general PQGON. And so our procedure is our claim, which we also prove in the paper. We don't just draw pictures. We rigorously prove this. The claim is the following. If you take a regular tessellation of hyperbolic space, here I've drawn it again in the 7-3 tiling, and you grow that slightly bigger, there's this growth prescription, that you can also assign boundaries to this picture and to this picture, and that this growth rule in the bulk what it does is it induces an inflation rule on the boundary. It defines for you an inflation rule of these boundary strings. And moreover, the inflation rule it describes is a unique invertible substitution rule with a irrational growth factor. So it's essentially, by definition, a quasicrystal. If you wanted to get an actual quasicrystal, because you notice these are just finite strings, if you wanted to get an actual quasicrystal, much like when we had our finite patches of Penrose tiling all the way back here, you need to take the limit as n goes to infinity. There's also more even sophisticated procedures for how to produce like many, many more tessellations, but this is the sort of idea. This is the simplest form of this idea. Bulk growth of hyperbolic lattices induces boundary substitution rules, and those boundary substitution rules have all of the properties of a 1D quasicrystal. And as you take the limit as n goes to infinity, you get something which is genuinely a quasicrystal. And again, you can make it more sophisticated. So that's essentially the claim. That's the main claim of this talk and of this literature, is that, if you want to go back to physics, you discretize ADS or something like that with these hyperbolic lattices. And the idea is at the boundary of these hyperbolic lattices are things that look like quasicrystals, and quasicrystals, as vaguely argued, but that can be argued more precisely in the paper, have some form of discrete scale symmetry. And so you have some sort of expectation that you have some sort of quasi-crystalline ADS CFT correspondence. And in the literature I dumped in the chat, you'll see that people have actually used this to show things. And I want to make a sociological comment. It's sociological, not super scientific. It's not like people noticed all of these facts about the scale symmetry, whatever, and then tried to cram ADS CFT into it. It was that, my collaborator had already, it wasn't that people saw ADS-CFT and they were like quasicrystal crazy people and they were like, let's try and do ADS-CFT with quasicrystals. They already knew that quasicrystals were like discrete scale symmetry. And they said, okay, well, if I truly believe that they have this discrete scale symmetry, then I would expect them to just naturally emerge at the boundary. And they didn't finally tune this prescription, because like I said, it's essentially unique. They didn't finally tune this procedure to make sure that they got quasicrystal. They just basically said, let's do sort of the analog of putting a finite cutoff on ADS. Let's see what emerges on the boundary. And they just they got all of this very naturally. It just showed up. They use it to make a prediction. So here's maybe the claim. Here's an experimental fact about ADS-CFT. Never thought you'd see a talk where people talked about experimental consequences of ADS-CFT. An experimental fact of ADS-CFT in the mathematical world is that if you take a regular tessellation, there's somehow a quasi-crystalline structure that describes its boundary. Anyway. So I will wrap up with this, and I want to address the question that was asked previously. And then I promise I'll wrap up. I won't go through all the rest of the slides. Is you might say, okay, this is nice, this is cute, but 1D is too simple. It's very topological, right? There's no curvature in 1D. What does it even mean? Like, where do the tiles live? It's kind of meaningless, right? Because again, 1D, everything's just about strings. Was this really a relationship between geometry and quasicrystals, or was it something else? And so then you naturally ask, can you identify a similar relationship in higher dimensions? And so you recall, for example, for a 3D hyperbolic space, there were 4 regular tessellations, including this 353 tiling here. And you might say, okay, if we want this fact to be true, or if this fact is true, we would expect it to hold in higher dimensions. And there's a conjecture of Latham Boyle, my collaborator, that the boundary of this 353 tiling looks locally like the Penrose tiling. And as the previous questioner asked, they said, oh, if you cut one of these higher tessellations and do some sort of cut and project, do you get the same thing? Well, the famous mathematician, William Thurston, had actually conjectured the same thing in private correspondence to Roger Penrose. So what he conjectured was indeed the exact same thing we found out as Latham Boyle. We didn't know this, but we were talking to Penrose about it, and he told us this was exactly the conjecture of Bill Thurston. So you're in good company with your conjecture. Thurston conjectured that if you took this 353 tessellation, you cut it along one of these things called a horosphere. So these are, I can draw a picture for you of a horosphere, maybe up here. A horosphere is something which is tangent to the boundary at one point. The reason why this is interesting is because you'll see that these things have zero curvature. So it's kind of like doing a cut. If you imagine the upper half space model, these are cuts at constant Z in the upper half space. So if you take one of these cuts, Thurston conjectured that there was some sort of cut and project method which would project into a Penrose tiling. Boyle's conjecture was essentially the same thing, although it was more in the spirit of this previous slide, where Boyle said if you take patches of the 353 tessellation, this icosahedral tessellation, you grow it out bigger and bigger into successive layers, that supports the quasicrystal. These two things are not obviously identical, but due to the unique and local rules that connect these two things, these two conjectures turn out to be equivalent. And so now let me just tell you the answer to this conjecture. I won't prove it. It takes too long, and we're a little bit short on time, and I don't want to trap people here too long. But the rule is essentially as follows. You just do it by brute force, and you'll learn some rules. So you take the 353, you take icosahedra, you close your eyes, you think really hard, you pretend you're living in 3D hyperbolic space, and you just start trying to grow these tessellations. Of course, having a computer also helps. You start to grow it, you try to identify what the boundary tiles would be, and then after a while, like that's how the experiment goes, you eventually come up with a theoretical mathematical rule, which is what we describe in the paper. And I won't subject you to that, but I'll just show you. This is a picture of the 353 tessellation, where in black, it's some piece of this 353 tessellation, and then in red is like the next layer, and I've projected them down to R2. And so then you stare at this picture for a very long time, and you go a little bit crazy. But you eventually realize that there's sort of three species of tiles which naturally live on the boundary. They look like this. These are not Penrose tilings. They might be locally equivalent to Penrose tilings in the sense of there's some redefinition, like, oh, maybe you cut off this piece here and you reattach it here. There's some way to connect them to Penrose tilings. It's not clear. Well, it's not clear a priori. I mean, I know the answer. What you can eventually show is that you can chop these three natural tiles down into a set of two, and that they define a consistent 2D aperiodic substitution rule. The substitution rule has all the right scale factors as the Penrose tiling. It has everything like that, at least numerologically. But what you find is that the scale factor of the substitution rule they define is twice that of the Penrose tiling. So if you were naive, you'd say, okay, we declare defeat. This is not the Penrose tiling. Of course, you could say maybe we just weren't clever enough. Maybe there's some even further refinement of our rules that gets you the Penrose tiling. Roughly speaking, maybe we've squared the Penrose tiling. But before I told you there was this uncountable infinity of Penrose tilings, people have also studied these global properties of Penrose tilings, and they can show that there exist Penrose tilings which form sort of closed circuits in the inflation space. So you start with Penrose tiling A, you inflate it, you get species B, then you inflate it again, you get C, you inflate it again, you get D, etc. And it's known that the smallest circuit that exists is an inflation where you go around 4 times and you come back to yourself. This is just one orbit in the space of all Penrose tilings. And we can show that the existence of this is not consistent with our tiling that we assign to the boundary. So in fact, you can show that there is no refinement that indeed produces Penrose tilings. So Thurston's conjecture, as well as Boyle's conjecture, is false. If you cut the 353 tiling, you do not produce the Penrose tiling. And so you say, oh, that's very disappointing. But then you realize, wait a minute, that's not disappointing, because what it actually means is we produced a new quasi-periodic pattern that is somehow intimately connected to the fact that it was in hyperbolic space. And this can be said about the other tessellations as well. So what you see is that there exists entire new families of quasi-periodic patterns which exist as boundaries of regular tessellations of hyperbolic space, and perhaps even more complicated tessellations. So I'll wrap up. Thank you for letting me go over time. Thanks everyone for your patience. So hyperbolic lattices and quasicrystals exist, and there's some relationship between them. I assure you it's all mathematically, technically provable. It's in the paper, but drawing pictures is much easier. New quasi-periodic patterns exist. So 2D quasicrystals with 5-fold symmetry that were all known to date were all the Penrose tiling or some close cousin. And we've produced a new 5-fold symmetric quasicrystal from these hyperbolic space techniques. And in the other cases, we produce even more new things that people haven't studied before. And we give a systematic method in the paper to associate families of these quasicrystals, much like the families of Penrose tilings, to boundaries of all hyperbolic tessellations, again, in a rigorous way. And these things have applications to physics. So do these hyperbolic lattice models, the discrete holography, as well as tensor networks and entanglement entropy. So here's some more lists of authors that I can single out of that list of authors. So with that, I thank everyone for the patience. I'm sorry for going over time. And yeah, it was really great questions.
Okay, thanks, Justin, for this very colorful and interesting talk. So there is a question in the chat. Can you read it, or I can read it for you?
Yeah, let me open up the chat window.
Okay.
Um,
It was a while ago, but
oh, okay. I'm really sorry to the person. We have representing groups. Group cannot be triangularized. Right. So the existence of the triangulation was not actually super necessary. It just gave a clean refinement. I would actually expect some sort of hmm. I would need maybe the question to be slightly sharper. If I see you're still here, if you would like to maybe try and sharpen it, I can answer another question. I can come back. I'm understanding the spirit of your question, but I'm at risk of rambling. Mention scaling of tiles.
I have a question.
Yes. What's that?
Okay. You mentioned that A4 lattice, if you look to certain projections of it, are related to Penrose tilings.
Yes.
Is it also true for A4 star lattice?
You mean the A4 star? Sorry, what's A4 star? You don't mean the
A4
dual?
star, yeah, it's the dual lattice, I think.
Oh.
It has point group symmetry S5.
Okay. So that's a good question. So I can give a somewhat trivial answer, which is since it's a regular, it's a lattice. Since it's a regular lattice in higher dimension, the cut-in project will produce something which will be, I guess, quasi-periodic. I have no clue if that thing. I guess I don't know the A4 star too well. I mean, it will include within it things which look kind of like Penrose tilings because obviously A4 is a subset of A4 star. But I guess you will also generically get more points than just those in the A4 when you do the projection. So it'll produce things which are like the Penrose tiling. I have no idea if it's a bigger set, a smaller set, or the same set.
So what is the symmetry of A4? Is it S5 permutation group or?
I believe so, yes.
Okay, A4 star is also S5, so I do not remember they may be, okay, I do not remember precisely. Okay, another, funny enough, there is a lattice formulation of n equal 4 super Yang-Mills, and its own A4 star lattice point group symmetry is S5.
I see.
It's just funny coincidence, maybe. The other thing is, it's a sort of semi-sociological question, if you don't mind. Actually, there is a very interesting paper from old times. I sort of recall it by Steinhardt and probably student Lu. Are you familiar with that? These Giri patterns versus Penrose tilings. Giri tilings versus Penrose tilings. These Giri tilings are sort of out product of the medieval period Islamic arts.
Mm-hmm.
They are very interesting, actually. Some of them are non-periodic, and at least, do you have any comments on those?
I think I know. So I don't know the specific paper you're referring to, but there are, for example, many things which are like the Penrose tiling. I'm not sure what the paper you're referring to is, so I can speculate. Where for example, maybe the aperiodic tile sets doesn't. Yes, thank you for the Wikipedia link. Where the aperiodic the tile set in those patterns does not so property about the Penrose tilings is they sort of force you to have only aperiodic tilings due to their local matching rules or due to their construction. But you can obviously produce close cousins where you just use the exact same tiles, but you sort of forget the arrows, the oriented arrows, and then that produces a much larger family of things. And obviously, if you're making, if you're a person laying down tiles in ancient times and making these I'm clicking the Wikipedia page now, these very beautiful tilings. If you're a person laying down tiles, you obviously wouldn't constrain yourself to have these local matching rules. So I could imagine that you would also produce, like that would be the more appropriate thing that would match onto these Geary tiles. I have no clue if that's what Steinhardt and his collaborator did. But.
The Steinhardt's paper's point was that, some of these tilings coincide with what we call Penrose tilings, and
I see.
Unfortunately, some cultures do not have a very good tradition of writing things that they find. They have more verbal tradition, oral tradition, and they don't tend to write things down. And sort of Steinhardt's paper, my reading of it was that, these people must have discovered some of the mathematics of these, irregular tilings, So it's an interesting set of ideas, honestly, to me.
Yes.
I tend to agree because, your audience, growing up in Turkey, same thing for Iran or some other places, are very familiar with this kind of patterns, from the old times, from the, as I said, from the Islamic art. It's very close to their culture.
Mm-hmm.
Yeah.
Yeah, I'm just scrolling. Obviously, I can't read this instantly, but yeah, this paper looks very relevant. Yeah, I could definitely understand that it must produce. Actually, I'm even more surprised. It seems like they might be claiming that they are. I can't tell if these Geary patterns are. They might even be claiming equivalent to the. Yeah, this is quite. Yeah, it's quite interesting.
They claim equivalence, and they say it is. I'm not looking at it right now, but I just talking from the memory. What I recall is, this kind of mathematics as well as the art. Art is the applied science of this mathematics, and this happened very frequently in the culture that we live through. The sort of things passed orally from generation to generation, and sort of they gradually disappeared. Forgotten. It is very misfortunate to me, unfortunate. And yeah, that's what Steinhardt was saying. Some of these mathematics must be known by, about 500 years ago. Yeah. I will look at it, me too, so it just reminded me.
Yes, I will add, is my screen still sharing? I guess. Yeah, it is.
Yeah,
So
see.
Indeed, it's actually interesting. Maybe I just use this as a jumping off point to this other thing is indeed you might think like the fact that it would be equivalent would actually be very important because to actually make a Penrose tiling is not as easy as you would think when you're following the local matching rules. So for example, you would see that if you were handed a set of these tiles and you tried to put them down, you'd see, oh, okay, well, I put one here. And then you'd see, okay, well, what would I put here? Well, if you go and you look, you'll see that you've completely screwed up. There's no way that you could actually fill this gap with another tile. So you can see that there's sort of these restrictions that can appear. And this is what I meant when they say they have these long range order. There's some other procedure, which is called these almond lines for decorating the tiles, which show that like you have to make these consistently long straight bars in these Penrose tilings if you want them to extend all the way out to infinity. And the reason I bring it up is because, yeah, if you were just a person laying down tiles without having any mathematical background, as one might think, then if you don't know at least the mathematics or some mathematics equivalent to the existence of these long, infinitely straight tiles which have to go through like this, you'd whenever you try to make these patterns, if you
Yeah.
were not just very lucky, you would get, you'd tile your blackboard and you'd try to tile the whole rest of your wall, and you might say, "Oh shoot, like I screwed up somewhere."
Yeah,
And
you
it
would
turns out
fail.
it was it was back at like move 7, right? So
Yeah.
yeah, it's an interesting point. I see there was a question in the chat that asked about scaling of tiles, and they say, "Can you mention any conformal tiling or familiar structure in hyperbolic space?" Let's see.
Okay.
So I mean, so I can say the following, which is maybe an answer in the spirit of what you're looking for. In my talk, I put regular tessellations in hyperbolic space, and I had quasicrystals that appeared on the boundary. There are mathematicians, there is at least one, I forget his name, I believe he was a PhD student of Conway, who studied actual quasicrystals in hyperbolic space. He has some definition of what it means to be a quasicrystal in hyperbolic space. So if I had to look for things having discrete scale symmetry, where scale symmetry means scales of ADS, not the boundary, then I guess that's where I would start looking. But that's the best. That's to the best of my knowledge the only thing I know. Are there other questions or comments?
Can I ask
Yeah.
one question, please?
Sure.
About this repeated application of inflation map.
Mm-hmm.
Do you know of any connection with dynamical systems theory? Because
Yes.
when people say crystals, they always think about space, but obviously, if you observe coupled oscillators stroboscopically, you get periodic, aperiodic patterns and all sorts of things. So I want to make a connection with chaos or dynamical systems theory.
Yes. Yeah. So I have been doing a very bad job of answering these questions, but the space of quasicrystals is very large and non-unified, so that's my excuse. The place I would look for that is, again, the work of Alain Kahn, who's studied these things. And indeed, the reason why that was the first thing that jumped to my mind is because Alain Kahn loves to understand the global structure of these quasicrystals, because they use a natural way of associating C-star algebras to them. And there's also obviously natural connections of C-star algebras to dynamical systems. So that's the first thing that jumps to mind. This is all explained in Kahn's book. The other thing that jumps to my mind is, in my particular case, okay.
Yeah, I want to keep this very simple. So I just want to look at the string of numbers here, and there
Yes.
are a finite number of them. I keep iterating. So what does it look like eventually?
Yeah. And what sort of measure are you looking? Not by measure, I don't mean the mathematical sense. Like what sort of
Some
question
sort
are you
of
trying to?
symbolic dynamics, and it shouldn't repeat. So
Yeah, like I mean, I can understand. I don't know how you would really make sense of dynamics. I mean, maybe you're saying I think of each layer as being somehow a system of points, and then I think of the next
yeah,
layer
so
as
each
being,
layer would be at each iteration you get observations from a non-periodic oscillating dynamical system.
yes.
Basically.
Yeah, I understand the formulation. I guess in our paper we would have the tools of how you'd set that up. I don't know really what I can say. I mean, I have some very coarse observables.
Well, it's
Like I know,
all open-ended, obviously. So I just want to be able to set up a dynamical system. Somehow its phase map will map onto this geometric structure you've drawn.
yeah, yes, yeah, that sounds totally reasonable. I would have no clue how to. Yeah, I don't have any sharp answers for you. I can tell you like relative numbers of how many of each tile species there are. I could, yeah. These are
Okay,
the kind
that's
of,
something to think about. It's just
yeah,
interest.
yeah. We do have full control over the tilings and everything like that, but I don't have good questions. So that's a good question.
Because there are synthetic dimensions and synthetic gauge fields in ultra cold atomic systems.
Okay.
So by applying periodic protocols of external time-dependent potentials, even if you have like a cold atomic system that lives in 2D or 1D, the entire system starts acting like it is living in synthetic number of extra dimensions, and it's subject to synthetic gauge field in these dimensions. So you can actually map dynamics in experimental literature. You can map dynamics to higher order spatial geometry. So that was
I
the
see.
motivation. So there's experimental relevance to my question.
I see. And is this at all related to these systems with Schrodinger symmetry, or are these different cold atom systems?
Yeah, Schrodinger, of course, yeah. Called out
Like
quantum mechanical system, and
in a harmonic trap sort of thing.
yes,
Like maybe
exactly.
Oh,
Yeah.
okay.
You have like time dependent, and there are experiments going on, and people are interested in it. So it's a nice application.
I'm very interested in
You
this for
talk to
other reasons. So yeah.
experimentalists, we devise a system, and you observe it, and you are actually kind of simulating a structure on a synthetic quasicrystal.
Mhm. Okay.
That gets you a lot of funding and etc., right?
Right. Well, yeah, I've been interested in this for other reasons, so I'd be very, yeah, I'll go and I'll do a quick Google search for that because it sounds very relevant. So, yeah, thank you.
All right, cheers.
Yes.
Yeah, I think there was another question. Yeah.
Okay.
Yeah, I was from a holography point of view. So because you now have a regular tessellation and that the conformal boundary, or in some limit, a conformal boundary would be a periodic sphere. So I was wondering if it's deeply related to the fact that like SYK model was also dual to the JT gravity in some sense that you have some disordered system which is dual to a gravitational system. Maybe a
Yeah, I mean, I want to say that's true, and not only do I want to say that's true, give me 1 second here. Let me link you these exact two references by Joanna's group. Yeah, so the first
yeah,
one,
I know that they use SDRG to get something like SDRG techniques to get the hyperbolic space and everything. I'm aware of these papers. I'm just
okay.
wondering, like, just for any discrete lattice, like, um, it's just something saying something very deep about gravity that the conform like there is something related to conformal field theory and disordered systems. Like the CFTs of any ADS dual would be some kind of disordered system. Its relation to chaos and everything. It's just a speculative idea.
No, I mean okay, now I better appreciate the question. Yeah, no, that sounds like something that I would like to be true given the mathematical facts I've proven. I guess the only thing to do now is to have somebody with the time to put to see if they can actually prove that, I guess.
Yeah.
Yeah. I yeah, thanks.
Sorry, I think I was a bit vague because
No, it's okay. No,
it's almost midnight here.
no, it's you didn't ask a bad question. I just more wanted to say like it seems like I think these are things that I'm very excited if people, especially those with numerical jobs, people who know how to use a computer much better than me, could start, simulating these things, testing. Because in some sense, what I've proven, or what I've told you today, and not actually proven, is I've shown you a bunch of facts which are approximately like a discrete form of, like, it's kind of like the kinematics underlying holography, right? Because I've sort of discretized ADS, but there's no dynamics involved yet. So it would be very interesting. And to answer your question, like the way that one might start to answer your question was they need to get dynamics involved, which is why I point to Joanna and others papers. And so sorry for my vague answer. It's only 10 a.m. here, so I have no excuse. But
No, it's fine. But in case of p-adic, like I mean, which would be the tree tessellation of this. So Parik, one of the people you referred, they did study some edge length dynamics and all that. But of course, for that you would need to study the Cantor set instead of quasicrystals, I guess.
right. And just this is not anything that, yeah. So just even to add on to your question, I've been wondering for a very long time, what is, if any, the relationship of all of this to the things like p-adic string theory or the, attempts to understand discrete holography that way. I assume they must be related, but I have no idea what the relation is. So
I can suggest you a paper in this, by the way.
Sure. Yeah, you can send
Yeah,
it to me
so
by
there is
email or here
yeah,
now. Oh yeah.
I can send the paper to you by email. Like I know one paper which explicitly, I don't know whether they explicitly talks about it, but they do, uh, they, I think they were studying error correcting the happy code on hyperbolic tessellations and found it was dual to infinitely coupled p-adic strings, like p-adic holograph.
Okay.
Yeah, yeah.
Okay. I see. I
I,
mean,
I
I
can
vaguely
email you.
see.
Yeah,
Yeah, thank you. Yeah.
yeah, yeah.
Can I ask one
Questions?
last question?
Yeah, yeah.
So at some point you mentioned C-star algebras. So I guess Alan Kohns was showing some relations with them. So and there is this holography relation, and in holography people study von Neumann algebras, and von Neumann algebra is a special type of C-star algebra. So what
Yeah.
kind of a relation can we, infer from these?
I have no clue. It's too, yeah. Again, I would love for there to be a relation, but these abstract objects are so big and broad that I would be scared to say anything.
I
Even,
see.
yeah, even off the record. Even if we stop the recording, I would be still too afraid to say anything.
I see. Okay.
Yeah, sorry. I'm happy if that people are generating so many questions. I hope everyone studies them, but I don't have answers. Thank you.
Yeah. Okay. Maybe we can stop the recording.